电脑是
要是
需要怎么选？
And the system is stupid. When I nominate, there's something I want to save in the chart. Then we can do then move, right? But in the system had two words, on the job, and with that move. Then if we photo that, the software is stupid, can have to repeat that. Because it's got to return. So that's the trick, you can reach the top. So now they're helping me
Okay, good morning. Welcome to the first seminar in the seminar series. It's my pleasure to introduce to you Professor Mahan from Stony Brook University. Over the years, Professor Mahan has done a lot of interesting work. She started her PhD by doing research on a very exotic type of quantum-based matter known as fluxons. She made a lot of contributions in that area. Then, as a postdoc, she kind of switched the direction to very complicated, very complex type of quantum matter, Fermi liquids and non-Fermi liquids. And the approach she uses is very unique, which really incorporates the very complex nature of the couplings in the system, and she's able to find a controlled way in many cases to deal with such a complex system. Today, she's telling us about some phase transitions in 2D Fermi liquids. Let's welcome. I think feel free to ask questions.
Thank you for having me, and thank you for the very long introduction. And it's a great pleasure to be here and to share my recent work. So the recent work is about Fermi liquid instability. Basically, it's about the transition out of the Fermi liquid phase into various different symmetry breaking phases. And I will show you that the transition can be switched from continuous to discontinuous. And the details of the work is in this paper, so you can check it online. Okay, so let me start with the very fundamental and important concept in condensed matter physics. That's the quantum phase transition. And we know it describes the phenomenon of the sharp change of physical property from of a system. Sometimes the change of the property can be very dramatic and in a sudden, such as the solid liquid phase transition or liquid gas phase transition, etc. And in general, the quantum phase transition can be classified into continuous phase transition and discontinuous phase transition. So the latter one usually describe a system, a gapped system at the transition point. And usually there is not too much interesting emergent phenomenon at the transition point. But differently, for continuous phase transition, the system is gapless and critical. And the system can have emergent scale invariance, and sometimes it can have emergent conformal invariance. So very large symmetry group can appear at the critical point. And those symmetries require the system behave in certain way. Say the correlation function has power law behavior, and the exponent control the power law belong to the universality class. So those exponent and power law behavior in the scaling limit is independent of microscopic details and short range noise. So they are the feature of the thermodynamic system, which can be probed and measured in experiments in reality. So this slide, I give you the two figures to show you very obvious difference between the continuous phase transition and discontinuous phase transition. So suppose we start with some phases described by some order parameter. And for continuous transition, as we approach to the transition point or critical point, the order parameter decrease continuously. And usually such a process is described by some power law behavior with the universal exponent. But for discontinuous transition, the order parameter change has a jump at the transition point. So this is very obvious. difference. So renormalization group is a very powerful framework to study the continuous phase transition and to extract the scaling behaviors. So it implements the coarse graining again and again on the system to remove the high energy or short distance noise. So say we start with some Hamiltonian, microscopic Hamiltonian, and the renormalization group method help us to remove those short range noise, but to keep the long range properties in the effective theory. So as we do this coarse graining again and again, we are left with effective theory with longer wavelength behavior. And in the end, we get an effective theory only contain the universal behavior at the long distance limit. So if such an effective theory has the scale invariance, then we are reaching the IR fixed point. So this is the fixed point to represent the universal physics of the system. Okay, so we can have various different type of fixed point depending on the RG flow around it. So for example, in this case, the RG flow given by the changing of the effective theory always run into this fixed point. So there's no flow out of it. So we say this is a stable fixed point. It corresponds to a stable phase because there's no perturbation can bring us away from this fixed point. And differently, if there is a relevant direction, so say we can add a particular relevant perturbation to this fixed point, and it will lead to runaway RG flow, runaway to other possible fixed points. Then we call it a critical point. And some of fixed point can have more relevant directions. We call them tri-critical point or multi-critical point. So if there's no fixed point, and for this type of RG flow, so the flow can go to different places, and in between, there's always a runaway flow go to infinite. We say there's a first order phase transition because we will never have scale invariance. We will never reach a system with scale invariance. So that's a first order. That's a feature of first order phase transition. Oh, yes, please.
Just to check, so the other points are not first order, only the last point is first order.
Right, right. Because as long as you are able to reach some fixed point by either fine tuning or not fine tuning, you can have a scale invariant theory. So that scale invariance gives you the non-trivial critical point.
So I have a question. So when you say there's no relevant perturbation, does it mean that is it spoken for example, a specific effective theory, or you really mean there should not exist perturbation for all kind of effective theory for this specific?
For particular fixed point, it should be described by particular effective theory. So if I give you some fixed point, you should ask me which what type of effective theory it is. So they always correspondence, yes. Okay, so we have these various different scenarios. So in a system, usually there can be multiple fixed points. And by tuning some parameter, we can realize the fixed point dynamics. So these fixed points can move inside the parameter space. And this will lead to the change of the nature of phase transition. So this is the physical consequence. And this is the theoretical tool we're going to use to detect or to verify if this physical consequence happen or not. So I will list several scenarios that the fixed point dynamics would change the nature of phase transition. So the first scenario is called a fixed point annihilation. So in this case, we have multiple fixed points in the system. Usually the one is stable fixed point, the other is unstable fixed point. And then by tuning some parameter, these two fixed points can collide and annihilate. After this process, we no longer have any fixed point in the parameter space. Okay, so the typical model to have this transition, to have this change is the Q-state Potts model. So it's a standard model studied a long time ago. And this fixed point structure is also very interesting. So it given another relevant direction for this RG flow. So this can actually tell us that by tuning the Q, the number of local Hilbert space, so we actually realize the change from second order phase transition to a first order phase transition. So that transition is the order to disorder phase transition in the Potts model. So that physical phenomenon can be explained by this fixed point dynamics.
Sorry.
Yes.
Earlier you said that the first order phase transition is identified with a single runaway flow to infinity, right? Then what's the second order phase transition mean?
Second order phase transition basically means you need a fixed point to land the system, right? So here we always have a fixed point with only one relevant direction. So that's the fixed point for the second order phase transition.
Okay.
And the blue one is the bottom bridge.
That's right.
So what's the meaning of the 2 points, when Q is bigger than 5? Greater than 5?
I see. So yeah, I didn't plan to dive into this. So for this scenario, fixed point annihilation, after they annihilate with each other, we can only find a fixed point in the complex plane. Yes, so for the real parameter space where the physical system live in, we cannot find any fixed point.
Yeah, then since it's first order phase transition.
That's right.
But then what's the meaning of the 2, what you call pseudo
Pseudo-criticality. Yeah, that means the complex fixed point, although they are not living in the physical space, they can still affect this phase transition. So the phase transition can have some property from which can be predicted from the property of these two fixed points. Yes.
So if you write down the effective theory around that complex fixed point, what would it be like?
So that effective theory will be non-emission.
Non-emission and pseudo critical.
Oh no, pseudo-critical means what happens in the real space. So that's why it's called pseudo-critical. It's not a true critical. Yes. So since it's first order phase transition, so it's not critical. It's not a continuous. But it's pseudo means there's some other fixed point very close to it, but cannot approach in the physical real system. So it affect it in some like a proximity way. So it's called pseudo critical.
So that means the non-formation effective theory yields complex fixed point somehow predicts the pseudo critical behavior in the real line.
Sorry, I'm worried about the time, so
Okay.
can we discuss offline? Because the point of this talk is not this, so. Okay, so let me give you the second scenario. So the point of this, I will focus dimensional 5-4 theory. So when D is less than 4, we know there is Gaussian fixed point and Wilson-Fisher fixed point for the order disorder phase transition. And for physical system, the true critical point is in the Wilson-Fisher universality class because this fixed point is more stable than the Gaussian. But when we increase dimension, these two fixed points merge to one fixed point. And above 4 dimension, the Gaussian fixed point is more stable. So if we measure the phase transition in D larger than 4, we have the Gaussian free universality class to describe the transition. So that's another example of the phase transition nature change. So we finally reached the third scenario. So this is what I'm gonna focus on in this talk. Because it was found in this Fermi liquid instability. So in this scenario, we only have single fixed point in the whole real parameter space. The fixed point, but it changes its instability. The fixed point is stability gonna change if we move the fixed point across the boundary of the parameter space. So it happens at a 2-dimensional, 2-flavor Fermi liquid instability. So it's an instability in other words, it's a phase transition out of this particular 2-flavor Fermi liquid phase. So I'm gonna describe this in very detail and start with this type of action. So notice the tuning parameter here to move the fixed point is the power of the fermionic dispersion. So before I go into the technical detail, let me talk of
Right, regarding the action earlier, your action seems to be non-dynamic. Is that a feature of Fermi liquids?
sorry,
Is there no derivatives in, or is this in?
this is in the momentum space.
Okay.
So I omega is the
Right, so
okay. Any other questions? Okay, so yeah, let me say a few words about why we want to study this type of dispersion. So recently, we are all very excited about the Mori system. It is a stack of graphene systems, and it can be so the graphene layers can be stacked in various different ways in order to realize different phase of matter and phase transitions, etc. So here there's a particular way of stacking called the Robinson stacking. Basically, it's ABC stacking of multiple layers of graphenes. And both theoretical and experimental shows that as we stack more layers, the band structure become flattened, more flattened. So and particularly the exponent of this dispersion depend on is exactly the number of layers of this stacking. So when this exponent is equal to 1, we have single layer and we have linear spectrum. And if we have more layers, then the dispersion is like this. So it's largely flattened around k equal to 0. So of course, in the real reality, we only have integer layers of system. So the spectrum or band structure can only have integer powers here. But theoretically, in order to study the difference or the effect of this higher power dispersion, we can do the interpolation between integer to alpha. So basically, we choose any real number of this exponent to study the interaction effect, especially the interaction induced instability of the Fermi liquid phase.
Is there the other side of the dispersion? Besides the opposite, is there another branch of the dispersion?
This two constant.
Oh, you mean this?
Yes, the band counting or is it we are
Oh.
the single band?
I consider single band.
Oh.
Yes. I see, because you are thinking like a drug ferment has kind of linear band catching, but in this case, I only consider single band. So say the other bands are very far away from this. And I only feel this band to some finite level.
But if I really transfer some these things together, I think I will usually I will have the other side.
I think so. Yes. Yes. Yes, and previously these people studied this also single band system. They found the dramatic change of the type of phase transition at the Fermi liquid instability once we change this dispersion exponent. And then here I used the renormalization group method to really have more reliable study on the Fermi liquid instability, particularly try to find the fixed point if it is a continuous phase transition. So in order to go to study to discuss the whole story, let me start with reviewing the Fermi liquid instability in single flavor fermionic system and due to interaction. And it's very straightforward to generalize to multi-Fermi flavor system. Okay, so we can start with the very basic Fermi C. As we know from quantum mechanics, due to the Pauli exclusion free principle, if we have fermions and one band, we're gonna fill those state up to some finite momentum kf. That's the Fermi momentum, and the total action for this whole system is basically quadratic in the fermionic field labeled by the frequency omega and the momentum k. And this is the free action is purely quadratic. And in the low energy limit, we notice only the fermions near the Fermi surface can participate into the low energy dynamics. So that's why the low energy effective theory can be written in terms of those low energy fermionic fields. So besides this frequency omega and the momentum relative to the Fermi surface q, these fermions are also labeled by the location on the Fermi surface theta, and the total action is a summation of all possible low energy fermions. So basically on the ring. And the integration measure now becomes the parameter of this, or the volume of the Fermi surface, or the volume of the zero energy phase space. So that's proportional to Kf. And we notice this action is not scale invariance due to this non-trivial area of the non-trivial volume of the zero energy space. Yeah, of course, we also expand the dispersion around the Fermi surface. And there's a way to define scale invariance action. That is this S0 divided by Kf. That is the average action per unit volume. So basically, we want to define such a scale invariant action, and so in this way, the Fermi C, the free fermion Fermi C can be viewed as a fixed RG fixed point. So the scale invariance is restored. Okay, then we want to consider the interaction effect. So many years ago, decades ago, Landau has a very beautiful Fermi liquid theory. So it provided a picture of how interaction works, how interaction induces the Fermi liquid phase from the free Fermi C. So basically, the free fermions, bare particles, is stressed by the interaction to form the quasi-particles. So the formation of quasi-particle makes the Fermi surface no longer sharply defined. And those quasi-particles acquire a finite lifetime, so they can decay in some rate. And if the interaction is not rotation invariant, then the Fermi surface can be deformed and break some rotational symmetry. And also it can shift the Fermi level. But as long as the quasi-particles are well defined, they have much longer time at zero energy, then the Fermi liquid phase is still well defined. That means, so if we can tune the interaction, increase the interaction, and the strong enough interaction can destroy this quasi-particle and destroy the Fermi liquid phase. That's the origin of the Fermi liquid instability. So this provides a physical picture. And now
Usually people often say, even if we finite time for the quasi particles, people usually say that these are sharp Fermi surface, right? You are calling polynomial Fermi surface.
yes, that's
This is just a convention.
yeah, that's true. Yeah, and that depends on the interaction stance and the weight. But
But as long as the quasi particles are well defined, then one way to define the Fermi surface is to look at the occupation member as a function of the momentum. If we see a discrete jump, that's the Fermi surface. In fact, this discrete jump will be given by the quasi particle residue.
and that that Fermi surface is defined by the quasi-particles. Yeah, no longer the original Fermi surface. Yes, I agree with that. Yes. Okay, so now I would like to use the RG framework to study the interacting fermionic system. So now our action contains the free part and the interacting part. So as we said, the free part is the quadratic in the fermionic field, and the quartic part has involved 4 fermions with different momentum K1, K2, K3, K4, and subject to the momentum conservation. So in total, they should have 3 independent momentum. But in the low energy limit, we can find there are, if we require all the fermions close to the Fermi surface, then the 3 independent momentum should have more constraint. So that is we can consider only the 2 different channels, 2 different scattering processes induced by this interaction. So the one is the particle hole channel. It describes the particle hole pair with very small momentum transfer scattered into another particle hole pair. And in the particle-particle channel, we have the particle-particle pair or Cooper pair with very small center of mass momentum scattered to another Cooper pair. So these 2 processes are allowed in the low energy limit. So we can write down our low energy effective action. Oh, yes.
Sorry, I have a question. I'm not sure it's related, but it's like, based on what I had taught, like, actually the momentum can be any opposite direction for the interaction, but somehow we are constrained to have like only equal and opposite like direction for the momentum. Is it like just a convenience, or is it like to ensure the overall momentum is stable? Yeah.
So you can solve the limiting. So you can consider the limiting case that all the fermions are on the Fermi surface.
Yes.
Then the capital Q and little q are exactly 0. So you can solve this this situation, and it gives you these 2 possibilities. So that basically identify the angle of 2 particles involved in this interaction. So that's why, thank you for the question. That's why I forgot to say this. So the interaction is basically a 2-patch process. Yes, compared to the different from the free part, which is summation of single patch. The interaction is actually summation of 2 patch. Yes.
But they cannot be in random places, they must be like opposite each other.
Right.
That's fine.
Maybe it's useful to clarify. In principle, they can be in random places.
Yes.
In space,
Yes.
but usually they are at high energies.
Yes.
If you focus on low energy, then they are
Because momentum must be conserved.
and close to the terms.
That's it. Yeah.
Yes, thank you. That's why the integration measure for the free part is the volume of the 0 energy space. That's the Fermi surface length. But in the interaction has this volume squared as the integration measure. So we have KF square in the interaction. And then we can follow the idea from the free fermion and define the scale invariant action. So now the scale invariant action can still be action per, if you have the picture of patch in mind. So it's still the action per patch. And that scale invariant action can define the fixed point of Fermi liquid phase. And by doing this, we actually define an effective interaction in the interacting fermionic system. So it's no longer the bare interaction. So it's enhanced by the zero energy volume. That's the KF if alpha equal to 0, if alpha equal to 1. And these are enhanced interactions are the effective interaction in our low energy theory. So that means if in general, in the original, very beginning action, if those bare interactions are irrelevant using power counting, then it can be largely enhanced in the zero energy. So, and these interactions are generally depend on momentum. So as I showed before, these three independent momentum are largely constrained due to the low energy effect, like the scattering should be very close to the Fermi surface. And then the interactions should depend on the angle of the two large momentum. And it can also depend on the very small momentum transfer and the center of mass momentum. When the momentum transfer is 0 in the particle Hall channel, this coupling function is basically lambda parameter in the lambda Fermi liquid theory. So he used this lambda parameter a lot to generate the effective mass and many effective phenomena in the Fermi liquid phase. And now we extend it to be a function of small momentum transfer.
Is alpha equal to 1?
Yes. So alpha equal to 1 is important in the sense that this volume should depend on alpha. This zero energy volume should depend on alpha. So you will see later on for generic alpha, we can define our effective interaction. Yeah. Oh yes, if we yeah, it depends on like if we fix mu or fix KF. If we use the KF or use mu, yeah. But I think, yeah, probably it's still proportional to KF in that case. Yeah. Yeah, that would, if we write in terms of KF, that would not change. But if we write in terms of mu, then I follow it. Yes. Okay, then our goal is to do the renormalization on the interactions. So the renormalization of interactions, of course, should include the many virtual processes and described by these loop diagrams. And we only study the correction up to one loop order. And in this talk, I'm gonna focus on the particle Hall channel. So I only study the renormalization of this particle Hall interaction or nearly forward scattering amplitude. And in the paper, we also study the particle channel. So, and in the later on, I even require the particle pair avoid to appear if we require some symmetry, like basically U1 symmetry, the particle conservation law. So this can be forbid, and we only need to consider this particle Hall channel. Okay, at one loop order, we can have this RG equation for the interaction in the particle Hall channel. So notice if Q equal to 0, there's no momentum transfer, then the right-hand side is exactly 0. that means the Landau parameter is exactly marginal. So you can have physical observables depending on the Landau parameter everywhere, because that's exactly marginal. But when we turn on this momentum transfer, it's no longer exactly marginal. It has a non-trivial RG flow. If we and we can solve this beta functional in certain way. So a very simple case is that we set the UV coupling function is a constant. And then as we lower the energy scale, the coupling function, the effective coupling function can have a non-trivial profile depend on the momentum transfer. And this makes sense because that large momentum transfer interaction is largely suppressed. And with the zero momentum transfer, effective interaction still stays the same. And this is a mathematical expression for the IR effective interaction. So using this interaction, we can compute many physical observables, such as density correlation function, etc. By using this effective interaction at tree level only. And besides, we can also study the collective mode of the system. That is just after doing analytical continuation from the energy scale to the real frequency, we can find out the zero sound mode is the pole of the coupling function. So the zero sound mode represent a collective of particle hole excitations that effectively deform the Fermi surface as a function of real time. And this is the zero sound velocity. We can see when f is larger than minus a half, then this velocity is well defined. So the collective mode is a well-defined excitation of the system. And before our RG framework, the collective mode was, I think the time is, so probably I can skip this slide. So before our RG framework, the collective mode was solved in using the kinetic equation describing the change of the phase space distribution of quasi-particle. But I'm gonna skip all of this. So the collective mode plays a very important role in the Fermi liquid instability, because as we can see, as we tune the UV coupling to attractive, then the collective mode firstly become a damped mode. So it would decay down to zero energy first, and then it's growing exponentially once the UV interaction is larger than some critical value. So that is a signature of the bosonic mode condensation that will lead to the Fermi liquid instability, because the boson or the collective mode usually carries some quantum number or break some symmetry. So its condensation will break some symmetry of the system, lead to the Fermi liquid, lead to the transition out of the Fermi liquid phase to some spontaneous symmetry breaking phase. Okay, so this is the what we have so far. We have a Fermi liquid phase beyond some UV interaction, and on the left side of this interaction, we enter some spontaneous symmetry breaking, and this point is the Fermi liquid instability. I listed the particle-particle channel phase RG flow diagram as well. So this is consistent with the previous Shankar's result, but yeah. Okay, so on this slide, I give more details about the Fermi liquid instability. Basically, I add the behavior of collective mode in different parameter regime. At this Fermi liquid instability point, so basically it's described by the Fermi surface coupled to a critical boson. So that critical boson will decrease the quasi-particle lifetime dramatically. and give us a non-Fermi liquid at this point. And beyond this point, if the interaction is isotropic, doesn't depend on any angle, we will get the actually phase separation in the ordered phase. It breaks the spatial symmetry, forms a domain of fermions in the real space. But if the interaction has some D-wave form, we have this Pauling instability and break the spatial rotational symmetry and give the nematic phase. That's the famous nematic transition. So far we have studied the interaction, RG of interaction to have this picture of Fermi liquid instability. And then we can consider the RG flow of chemical potentials. So the interaction would also shift the chemical potential. Pictorially, if we have repulsive interaction, in the real space, the fermions are spread out. So in the momentum space, they are more clustered. So the chemical potential gonna be lowered if we have repulsive interaction. But if we have attractive interaction in the momentum space, the fermions are more spread out. So the chemical potential becomes bigger, effective chemical potential. And it's completely encoded in this one loop diagram. And we can use this one loop diagram to produce the RG equation for the chemical potential. So from this RG equation, okay, from this RG equation, we can find that when lambda is, or the Baire interaction is attractive, there's always runaway RG flow. But when lambda is positive, we can find a fixed point at a particular rescaled chemical potential. But these two will not, this result will not change the Fermi liquid phase in any way, because at the fixed point, the effective action is scale invariant, of course. But even though we don't have any fixed point, we can still, as long as the Fermi surface exists, we can still expand our dispersion, low energy effective action around the Fermi surface, and the changing part is only the Fermi velocity. And we know the Fermi velocity is not universal anyway. So, and this flow of chemical potential will not affect the Fermi liquid phase, and also it doesn't affect the Fermi liquid instability as well.
Question?
Yeah.
This chemical potential is not directly related to the size of the Fermi surface.
Oh, you're saying, are you thinking about Hydro theorem? Oh, so I think I don't require particle number conservation in this case. Like I can tune the chemical potential, and the particle number can come in and go out as long as lower energy. So the low energy is the only criterion here.
So then what's the relation between this chemical potential and the Fermi surface size?
I don't think they have a very so Fermi surface size is related to the total particle number, right? And the total particle, and I think this chemical potential can relate it to the Fermi surface size. And the Fermi surface size change. That means my system has different number of particles. So like we consider the ground canonical ensemble, so the particle number can change, like we cannot fix the particle number in the framework.
And you can think about it.
Yeah. Okay, so it will not affect the Fermi liquid instability. Because that instability always happen at attractive interaction. So, but things would be different if we have multiple Fermi flavors, because we can have more Fermi liquid instabilities, and one of them can have a chance to have scale invariance. So so this slide, although it contains many equations, but the only thing I changed is I add a flavor index for every fermionic field. So now the chemical potential can have flavor, can depend on flavor, and the interactions can depend on flavor as well. Okay, and now I can define the Landau parameter in this way. So this is what I say the alpha enters. Yes, these are all possible interaction vertices. So to simplify the problem, I only consider the U2 symmetric system. So if we impose the U2 symmetry, then the chemical potential are forced to be equal to each other, and the interactions are also forced to equal to each other and equal to the summation of the interflavor interactions. And in this way, we are able to solve our IR effective interaction in a very straightforward way. And use such IR interaction, I'm able to compute the physical quantities. I'm able to compute physical quantities. So for example, I can compute the spin-spin correlation function. And it turns out the IR effective interaction F2 of F2 contribute largely to this spin-spin correlation function. So basically that F2 characterize the difference between flavors. But the density correlation function is largely contributed from the F1. So the F1 basically measures the overall effect of all the flavors. Okay, then if all the interactions, effective interactions, correlation functions are finite, we are able to be inside the Fermi liquid phase. But once one of them become singular, we can encounter the instability out of the two flavor Fermi liquid phase. There are two possibilities now. So that means we have two instabilities now. So one is driven by this F plus F1. So as F1 describe the overall effect of the two flavors, then this instability is somehow the density instability. It causes the spontaneous symmetry breaking of the spatial rotation. Basically, the two Fermi surface are gonna deform in the same way and cause this instability. But there's a new instability, type 2, that is driven by the dramatic change in the difference between flavors. So that's lead to a spontaneous symmetry breaking of the flavor. So if the flavor is spin or valley, then that indicates some spin or valley polarized state. So there are two possible instabilities. And then we can also study the collective mode in the Fermi liquid phase. And besides this density collective mode that describe the deformation of the two Fermi surface in the same way, we have a new collective mode that describe the two Fermi surface deforming in the opposite way. So basically delta n plus and delta n minus have the opposite sign.
Question?
Yeah.
So for the first instability, the rotation symmetry is broken to what?
The rotation symmetry depends. That's the same as what I described before in the spinless fermion. So for the isotropic interaction, we have the phase separation, and for the D wave, we have nematic condition. Yeah, that's the same. Yes. The new thing is instability 2. So these two instabilities are driven by the change of the damped mode to the exponential growing mode. So instability 1 is driven by the change of density mode, but the instability 2 is driven by the change in the spin mode. So that's the kind of phase diagram spanned by the F1 and F. So we can clearly see like it has richer structure than the spinless or single flavor fermionic system. Okay, then we can, besides the interaction, we can study the RG flow of chemical potential as well. Now we can find the fixed point for the chemical potential. So remember the two chemical potentials are the same. So the fixed point is at a we scale the chemical potential at some particular value depending on the summation of the UV interaction or the density or the interaction represent the overall density. So that means at the instability 2, we can have a scale invariant transition. That's the transition leads to the flavor polarization. So that means we have a chance to find some scaling behavior at the transition from the fermi-liquid to say valley polarization or the automagnet. So if the interaction is isotropic, this instability 2 would lead to the ferromagnetism or valley polarization. So it immediately empty one Fermi surface and fill the other Fermi surface. But if the interaction is angular dependent, then the spontaneous symmetry breaking would lead to a flavor splitting band structure, meaning that the different flavor would have different orientation of the Fermi surface. So that's an example. One example is the automagnet. So this is a very interesting result that this instability can have a chance to get a scale invariant properties.
Question?
Yes.
There's some previous literature starting the ferromagnetic transition in the metal saying usually is discontinuous. And here is continuous.
That's a good question. So this comes to this slide. So we haven't say this fixed point is stable or unstable, right? So here, by tuning this alpha, we can change the stability of the fixed point. So from this figure, the vertical axis is we scale the chemical potential. The horizontal axis is the alpha, is the exponent of the dispersion. So when alpha is less than 1, that means means any real value less than 1, the fixed point is attractive. So the RG flow will go into this fixed point. That means given another interaction direction as a relevant perturbation, so this is a critical point. But when alpha is larger than 1, the fixed point is no longer stable, it's unstable. So we can keep track of the RG flow go to infinitely large chemical potential or 0 chemical potential. So this indicates a first order phase transition. And interestingly, at this first order phase transition, one of the Fermi surface is immediately depleted. So after the continuous phase transition, the two Fermi surface can still have some finite feeding, but at the first order phase transition, there's immediately depletion of one Fermi surface at the transition point. So
why is this a discontinuous transition instead of a multi-critical point?
Multi-critical point also indicates some instability in like fine tuning, right? So if you don't do fine tuning, you just so let's say we land at some mu initially, right? And if alpha is less than 1, I can, as I do RG, as I go to low energy, then I will land on this fixed point. But for this case, if I don't do fine tuning, I just flow away.
But if I do fine tuning, then
Yeah, then you can, yeah. You need fine tune the chemical thing, yeah.
also this alpha, if alpha is larger than 1, then alpha equal to 1 will be generated.
Generate, what do you mean?
When we integrate all high energy modes, alpha equal to 1 will always be generated. That's compatible with the locality and destination.
Oh, I see. So you mean the alpha equal to 1 term will be generated? So I thought about this. I think that would not happen. Oh, in the sense that no matter what value alpha is, we always do expansion around the Fermi surface, but we always get a linear dispersion, no matter what alpha value is. So what matters here is if the complete depletion happens or not. So if the depletion happens, then alpha enters the result. But if depletion doesn't happen, then you always have the linear dispersion around the Fermi surface, so alpha doesn't matter.
So suppose in the kinetic term, if that's the k to the 2 alpha, I also have another term that's just the k squared. In this case, what happens?
In this case, you still get linear dispersion around the Fermi surface. You start with the same.
But in terms of the depletion, does it happen?
In terms of depletion,
If the kinetic term has 2 terms, k squared with 1 coefficient,
mhm.
k to the 2 alpha with another coefficient. So should be alpha bigger than 1.
And that I would say, I'm not sure. So that alpha would enter some place, right, in the effective interaction, etc. So in that case, I cannot say like how alpha enters in that interaction, effective interaction. Yes.
But I think that's such a case if alpha is really larger than 1. Interaction will generate k squared.
But if you start with the effective theory around the Fermi surface, that doesn't matter then. So like you don't do power counting to say that the term is more relevant and can be generated, because you always have this linear dispersion and right. Yeah. And alpha enters into like Fermi velocity and those things, and you won't say some Fermi velocity is more relevant than the other one. It's like coefficient, it's not for the power, it's not for power counting, it's more relevant. Yeah, that's what I think about this problem, yeah. But, yeah. Okay. So this is the new scheme, the third scheme I've talked about in the introduction. So we only have one fixed point, and that fixed point can change its stability by tuning this exponent in the dispersion. And by changing its stability, we can change the nature of phase transition. Say when alpha less than 1, the transition is continuous. Alpha larger than 1, the transition is first order. Because we always can flow to infinite. Okay, I think I'm run out of time. It's 12, but I can. Okay, so based on the knowledge of the U2 system, we can also study the U1 cross U1 system. And in this system, the interactions and the chemical potentials are not. They basically can choose an arbitrary value in the UV. They don't have any constraints among them. And we can study the RG flow of interactions. We can study the collective modes. There are also two collective modes at some particular interaction strengths. And these collective modes can have different behaviors. So this is the numerical result of the collective mode. And we can see for tuning some parameter would change the range of the well-defined collective mode, which is so blue and orange are the well-defined collective mode. Green is the damped mode, and red is the unstable growing mode. So the region between the red curve happen is the stable Fermi liquid phase. And beyond this, we have the unstable growing mode that would trigger the Fermi's liquid instability into some symmetry breaking phase. And in this case, we can also find the same physics. So I don't need to repeat. When alpha is less than 1, we have the stable fixed point. When alpha is larger than 1, we have unstable fixed point. But what I want to say is, no matter what the interaction is, so when we measure the continuous phase transition at alpha less than 1, one can always find this universal data. So A plus A minus is the amplitude of true Fermi surface deformation of the collective mode. So remember, the collective mode describes the oscillation of the Fermi surface. It deformed the Fermi surface. And it in one so so the deformation of one Fermi surface can be different from the other one, and this ratio characterizes how they deform the relative to each other. And this ratio at the transition point, at the critical point, is determined by the ratio of the chemical potential. So that's the universal result at the continuous phase transition. Okay, so in conclusion, so in this work, we study the Fermi liquid instability. So I reviewed the single flavor Fermi liquid phase, and its instability is driven by the condensation of collective mode. And I also talk about the two flavor Fermi liquid phase. Its instability is driven by the so-called density mode or the spin mode. So the condensation of the spin mode can lead to some flavor polarization phase, and the transition point has this change is continuous when the dispersion is less quadratic and is discontinuous otherwise. And then we propose there can be some universal data at the continuous transition. And this theoretical result can be possibly verified by experiments in Moray system or automagnet system in the Fermi liquid to other phase transition. So using the same method, we can study various different things. Since our RG taking care of the whole Fermi surface, so one can study the non-circular Fermi surface, which is more realistic in nature. And we can also study the instability of the automagnet and the impurity effect in all of those metallic phases. With this, I will thank you.
Thank you for the very impressive talk. Any further questions?
Yeah. So, just now you mentioned that you use the normalization, RG flow to study the Fermi liquid. What if the Fermi liquid is prone to like external interactions, for example, like black matter reactions? So is it possible to study it also?
I see. So you have light interacting with the Fermi surface. Then I would think your light is some bosonic field, and you can add some. So if you treat the whole thing as the as your system, then you need to introduce fermion boson interaction and adding to that. And I think it would be more complicated to study,
Okay,
but in principle, it's possible.
okay, so basically we need to modify the action integral.
Yes.
Okay.
Yes.
Further questions?
So I have a question about your choice of U2. So U2 means like two species of two flavors. So it can either mean like the electron spin up, spin down, or very
Yes.
A or very B, right?
Yes, that's right.
But what if like we consider both like both spin up, spin down, and very A and very B, like
Oh, you mean-
U4, U2 cross U2.
Yeah, you have four flavors and yeah,
But
they can have different symmetry, like you can have U2 cross U2 and U4, something like that.
is it needed for the low end? Because we are considering low energy cases, do we still need to consider U4 or is U2 enough to provide?
Well, that depends on your system.
Okay.
So the symmetry is determined by your target system, right? Yeah, depending on what you want to study, like if the system matches with your expectation.
And another thing I'm sorry, and I have another thing to clarify is that you say like high energy equals to short range and short distance, or low energy equals to long distance, right? But to me, like because I'm doing like I studied time then so I was like, oh, it's the similar long distance means long range. You know, right? It doesn't mean that.
Oh, that's not
It
that,
just means the wavelength is long and for the energy is slow.
that's
I
right.
see. Thank you. Yeah.
Any other questions? Okay, if not, let's thank you for this.
这个上面会有人问问题。
That's all it's